The density of iron. The crystal structure of iron is body-centered cubic at temperatures below 910 degrees C and face-centered cubic above. Compute the ratio of the densities of the two structures under the assumption that the atoms can be considered to be close-packed hard spheres, the diameters of which are the same in both structures. Okay, so in body-centered cubic structure, we have the nearest neighbors, the one at the body center and the one at the corners. So the body diagonal is a square root 3, where a is the lattice constant. So we have the atom in the middle that has diameter 2r, and the two atoms at the two corners facing each other across the body diagonal at the corners. So we have a 1/4 of each circle, basically, that will be on this plane for the cross section of the sphere. So we see that the body diagonal, if the nearest neighbors touch, so basically we have the assumption that the nearest neighbors touch. That's the close packed assumption. The nearest neighbors touch. So we see that 4r is a square root 3, therefore r, the radius of the one of the atoms should be a square root 3 over 4 in that case. So we find that the lattice constant for the body-centered cubic structure should be then 4r divided by square root 3. And if we go above 910 degrees C, so this is temperature less than 910 degrees C. And now if I go above 910 degrees C, iron turns into face-centered cubic. Now the nearest neighbors are at one of the faces of the cube. So we have the atom at the face center and the two atoms at the face diagonal facing each other at the corners. So the total distance between the atoms at the two opposite ends of the face are 4r. So if a is the lattice constant here, so a is our lattice constant, a square root 2 would be equal to 4r. So I would have the radius of one of these atoms to be a square root 2 over 4, or the lattice constant for the face-centered cubic structure would be 4r divided by square root 2. So in the case of the body-centered cubic structure, I had this to be 4r over square root 3. Now for the face-centered cubic structure, it's 4r divided by square root 2. Now the next thing I have to determine is the number of atoms per cell. For the body-centered cubic structure, number of atoms per cell is going to be 8 atoms at the corners, 1/8 of each inside the unit cell, plus 1 at the body center, so the total will be 2. And for the face-centered cubic structure, the number of atoms per cell will be, once again, 8 atoms at the corners, 1/8 of each inside the unit cell, and 6 atoms at the face centers, half of each inside the unit cell, so the total will be 4. Now, what is the density of the body-centered cubic structure? So we have 2 atoms per unit cell, so we have twice the mass of iron, twice mass of one iron atom, divided by the volume of the unit cell, which is a cube for the body-centered cubic structure. So we see that ABCC was 4r over square root 3, so this will be equal to twice mass of iron, 3 square root 3 divided by 64 r cube. So that is the cube of 4. 4 times 4, 16 times 4, 64. 64 r cube and 3 square root 3 on top. And as for the density of the face-centered cubic structure, I have 4 atoms per unit cell. So 4 times the mass of iron atom divided by A FCC cube. So this will be equal to 4 times mass of the iron atom. Now I have 4r over square root 2 for AFCC. So this will be 2 square root 2 divided by 64 r cube. Now I'm ready to compare these two densities. So if I take the ratio, the density of the BCC structure divided by the density of the FCC structure, this will be, because I have 3 square root 3 on BCC and 2 square root 2 on FCC, the ratio of 2 mass of iron 3 square root 3, so it's going to be 2 times 3 square root 3 divided by 4 times 2 square root 2. 4 times 2 square root 2. So I find this ratio to be, because these 2's cancel, 3 square root 3 divided by 4 square root 2. So if you calculate what this ratio is numerically, rho BCC divided by rho FCC is roughly 0.919. So this is the ratio of the densities. Okay, so we talked about iron, two different phases, body-centered cubic phase for temperatures below 910 degrees C, and face-centered cubic phase for temperatures above 910 degrees C. Now, under the assumption that the diameter of the hard spheres don't change, the diameters of these hard spheres don't change, we have the same radius of the sphere in both structures, and we're using the close-packed approximation, which means the nearest neighbors touch. So where are the nearest neighbors in body-centered cubic structure? Those are the atoms facing on opposite sides of the body diagonal at the corners and the one at the body center. The distance from one corner to the other corner in the opposite side of the body diagonal is a square root 3, where a is the lattice constant here. So we can basically see that the radius of one of these spheres should be a square root 3 over 4. Or the lattice constant for the body-centered cubic structure is 4r divided by square root 3. And for the face-centered cubic structure, the nearest neighbors are at one face, the one at the face center and the two at opposite sides of the face diagonal, which are at the corners. So the distance between these corners is a square root 2, which is equal to 4r. So r is a square root 2 over 4, or lattice constant for FCC structure is 4r over square root 2. There is one more difference between these two. In body-centered cubic structure, number of atoms per cell is 2, whereas in FCC it is 4, because we have 1 at the body center, 8 at the corners, 1/8 of each inside one unit cell, giving us 2 for body-centered cubic, and 6 at the face centers, half of each are in the unit cell, so we have 3 plus 1, 4. Then we can calculate the density as twice the mass of iron divided by a cube BCC, or 4 times the mass of iron atom divided by a cube FCC. When we do this and take the ratio, we find that rho BCC to rho FCC ratio is about 0.919.